Now, the first intermolecular force that we encounter is the ion dipole force. And this is simply an attractive force between the ions, generally dissolved ions in a solution, and polar molecules, which are generally the solvent molecules here. Now, the attractive force is between the full charge on the ions and the partial charges, positive or negative, on the polar molecules. So an example of this is simply table salt in water. So if we take sodium chloride and dissolve it in water, we have then the sodium ion and the chloride ion dissolved in water. And water will arrange itself so that the partial negative end of the water molecule surrounds the positive sodium ion, and the partial positive ends of the water molecules will arrange themselves around the negative chloride ion. And then those interactions there are the attractive ion dipole forces. Now, this is really important because ion dipole forces are the strongest intermolecular forces. They can be up to about 10% of covalent bond in some cases. And ion dipole forces are the reason for the solubility or lack thereof of ionic compounds in polar solvents. So what do I mean by that? Well, when an ionic compound dissolves in a solvent, let's say water for example, in order for the ionic compound to dissolve, you need to break the ionic bonds that are holding the two ions together in the solid form. That requires energy. So where does that energy come from? Well, that energy comes from these ion dipole interactions. So if the energy that you gain from these attractive ion dipole interactions is greater than the energy of the ionic bonds, then the compound will be able to dissolve because they have enough energy to break those ionic bonds, which are simply an electrostatic attraction themselves, and you'll be able to dissolve the ions into the solvent. However, if the amount of energy that you get from the ion dipole interactions is less than the ionic bond strength, then that compound will not be soluble in that solvent. So this explains why compounds like lead iodide are not soluble in water versus other ionic compounds that are. In one case, in the case where things are soluble, you gain enough energy from the ion dipole forces to overcome the ionic bond strength, but for insoluble precipitates, you do not have enough enough energy from the ion dipole forces to overcome that ionic bonding. The second force here we'll talk about is dipole-dipole forces. Now, if you were paying attention, you might notice that this isn't the next strongest. Hydrogen bonding is actually the next strongest. But I want to talk about dipole-dipole forces first, and that will make sense when I talk about hydrogen bonding. But dipole-dipole forces are simply attractive or repulsive forces between polar molecules now. So not between full charges on ions and partial charges, it's now between partial charges of various polar molecules. And an example here is acetonitrile, CH3CN. I can draw it out and show that it's a polar molecule that has a net dipole that points towards the nitrogen. So the nitrogen end is the partial negative end, and the carbon on the left is the partial positive end of the molecule. And in the solid form, when acetonitrile is packed together in an ordered array in the solid form, what we see is that the molecules are ordered in such a way as to maximize these attractive interactions. So it's arranged such to maximize the attractions between the negative end of the molecule and the partial end of another molecule. And those molecules are all held very tightly in that ordered arrangement that maximizes those attractive forces. However, once we move into the liquid form, now there's more freedom of motion, so we end up with a variety of attractive forces and repulsive forces that are present. Now, one thing to note is that the magnitude of the dipole-dipole forces increases with increasing dipole to the molecule. So we can show this with a number of different molecules. If I show here, we've got propane, and then I have dimethyl ether. and acetaldehyde and acetonitrile shown here. And what we'll notice is that, well, we don't really have the one all the way on the left here is not a polar molecule, and we have just carbon and hydrogen bonds here. Perhaps we might have an extraordinarily tiny net dipole moment, but a very, very small one, whereas the other three have polar bonds to the oxygens and a net dipole moment, which is illustrated with the bond dipole, with the net dipole drawn as shown. And what we'll see here is these are all approximately the same molecular weight. And I highlight that just because when we talk about dispersion forces, we'll note that molecular weight affects that intermolecular force. But here, we would say that they're all approximately the same molecular weight. Now, their dipole moment increases from a very, very small dipole moment of 0.1 all the way up to 3.9. These are units of Debye. It's a common unit for dipole moment. And so we can see acetonitrile is has the greatest net dipole. And if we look at their boiling points, which remember is a measure of the strength of the intermolecular forces, we'll notice that with almost no dipole moment here, we have very, very, very small dipole-dipole forces. Really, we would say we have essentially none for propane, and it has a very low boiling point. As we increase the dipole moment and thus increase the amount of partial negative charge on one end of the molecule and the amount of partial positive on the other end, now you'll see that the dipole-dipole forces increase, which leads to an increase in the boiling point. So dimethyl ether boils at negative 25 degrees Celsius, acetaldehyde with a larger dipole moment boils at 21, and then finally acetonitrile with the highest dipole moment boils all the way at 82 degrees Celsius. So the overall takeaway here is that increasing polarity, increasing molecular polarity results in increasing dipole-dipole interactions and thus increasing the boiling point. And so for molecules of approximately equal mass and size, the strength of the intermolecular attractions increases with increasing polarity. Just another way of kind of saying the same thing. Now, in addition to boiling point, dipole-dipole forces are also the reason for the solubility or lack thereof of non-ionic compounds in polar solvents. So here, if we look at this example, here we have three liquids in a test tube. And you'll notice that the top one is hexanes, the middle is water, and the bottom is carbon tetrachloride. Now, water is a polar molecule, and between water molecules there are a lot of dipole-dipole forces and some hydrogen bonding, which we'll talk about later. But hexane is a completely non-polar molecule. It's essentially zero dipole moment. Carbon tetrachloride actually has a zero dipole moment of being fully symmetrical. And both of those are non-polar. They would not have any they would have essentially no partial negative or partial positive charges, so they could not participate in dipole-dipole forces. And as a result, when mixed with a polar liquid, they will not mix with it because they are unable to participate in dipole-dipole forces. And if they did mix, they would disrupt the dipole-dipole forces that already exist between the water molecules. And so these liquids are termed immiscible with water. Contrast this with acetone, which is a common nail polish remover, and water. Those are completely miscible. And that's because acetone has a net dipole moment, which points towards the oxygen. And so it has a partial negative and a partial positive ends to its molecule. It's a polar molecule from that polar CO bond. And it's able to participate in these dipole-dipole forces with water, and thus we have then attractive interactions between the water and the acetone that makes this fully miscible. Another example here is ethanol. This is a very common and familiar substance. Here we have a polar molecule as well. Carbon-oxygen and hydrogen-oxygen bonds are polar. We have a net dipole moment that points towards the oxygen. And so again, we're going to have interactions, dipole-dipole interactions between the ethanol and the water that makes the ethanol soluble in water. And so the overall takeaway here is that it's often expressed as like dissolves like, where what we mean is that species that have similar intermolecular forces, so dipole-dipole or something of that nature, those tend to dissolve in each other or mix well with each other, whereas species that have different intermolecular forces, so dipole-dipole versus not having dipole-dipole forces, those are immiscible with each other. And so we can see here that whereas ion dipole forces were the explanation for solubility or not of ionic compounds in polar solvents, dipole-dipole forces are the reason for solubility or not of non-ionic compounds in polar solvents.